OK, we'll go ahead and get started. So hello, my name is Christina Lee, and I am here to talk to you about testing, specifically testing. Now, in case it wasn't clear, my talk is about testing. Just wanted to make sure we were on the same page there. And when this was first proposed to me, when Hadi first said, hey, do you want to talk about testing? I said, absolutely not. And of course, the reason I said this was because people have a lot of opinions about testing, and I have a very strong sense of self-preservation. Now, when I told my friends that I had been talked into doing it anyways, most of their responses were something like this. And this, of course, begs a very important question, which is, why am I still friends with these people? But it begs this secondary question as well, which is, why is testing such a hotbed of controversy? And I have some opinions on this, but I think it all begins with the fact that at least where I work in Silicon Valley in San Francisco, in the heart of one tech scene, if you say that you don't want to test or that you don't believe in testing, it is shunned. You are considered a sloppy engineer who is playing it fast and loose with their code, and it's considered really unprofessional. And as such, very few people would ever question the value of testing. Now, when you consider a definition of testing like this one, that testing is just executing a program with the intent of finding error, then this sort of behavior and this sort of opinion makes a lot of sense. In that, if you ship a program and you never even attempt to find errors, you just stick your head in the sand, that's pretty ridiculous. So if we look at it in this way, it makes a lot of sense that testing is good and you should be doing it. Of course you should. This all is clicking into place. Where then does this rift come in? Well, I have a hypothesis, and that's that with the age-old adage, the devil is in the details, specifically the implementation details. Now, if we take a look at the common test case of unit tests, these should look pretty familiar. Here's one set up in the arrange, act, and assert, which is a default way of doing unit tests. It looks pretty straightforward. But of course, anybody who's done testing knows that unit tests often are not enough to prove correctness. And they often need to be accompanied by something called integration tests as well. Now, integration comes from the word integrate, which simply means to combine. So whereas unit tests look like that first one, where they're pretty self-contained, integration tests usually occur at the boundary between two separate pieces of code. Now, this is, of course, a gross oversimplification of the many forms and complexities of testing a large system, but for our purposes, we can begin here in our testing journey. And so this sounds pretty straightforward. Right now, what we're talking about is taking one piece of code and testing it, and then making sure that when you combine it with something else, it still works. So where does it get complicated? Well, it turns out that a lot of people think that testing should be automatic, and I actually tend to agree with them. I believe this too, that testing should be run automatically, and usually that takes the form of testing on each commit. So this is something that I practice as well, but one of the externalities of this is that if you test on every commit, it means that you get slower commits. And of course, if your commits are slower, then people are more prone to shoving a lot of things into the commits because that process takes longer and they don't want to have to go through it quite so often. Of course, there's also this idea of the fact that it would be impossible for us to test every solution that could go through our system. So this is just math at play, where the number of data representations there are far outnumbers anything we could ever test. And as a result, what happens is that we have to selectively choose what we want to test. And because we are humans, and humans are hardwired to operate in a world that they assume is kind, because otherwise we would lose our mind, What we usually do is we pick normally distributed inputs. And so what that means is that for the case of an integer, we might cherry pick something like the numbers 5 and 17 because they seem reasonable. And then we would test the common edge cases like 0, -1, maxint, and minint. But unfortunately for us, there are a lot of systems in the world where failures are not uniformly distributed. For instance, finance falls into this case, where a lot of failures are actually catastrophic. And so very few of us are probably testing our system on the assumption that someone wrote a bug that brought down the server the day before Christmas, and our app is now operating without a backend. This is not something that would usually come to mind, but it is something that happens. And as such, we can find ourselves in this place where we have written tests against a piece of code, and we have shipped that code, and yet the code still breaks in production, and this makes us feel like our investment was not a wise one. Now, there's also this other class of problems, which is that test code is source code. You need to architect it, you need to maintain it, you need to refactor it. It is source code. It is just source code that you are not shipping, usually, to your users. And as such, if you are a software engineer, you are making a lot of architectural decisions about it. And this can make you prone to something called test-induced design damage. Now, this is a term coined by DHH in a blog post about 5 years ago, and he includes this very meaty definition of what that entails. And I'll just sum it up for you, which is that his definition here is that test-induced design damage is what happens when the pursuit of easier, faster, or more unit testing coverage warps your code through needless indirection or complexity. Now, a very, very trivial case of this, if you are an Android developer, is this annotation, which is visible for testing. You can go to the Android documentation, and you can see this definition of it, which is that it denotes that the class, method, or field has its visibility relaxed so that it is more widely visible than otherwise necessary in order to make code testable. And of course, this gets worse, which is my favorite saying in presentations, because the very next line is this one, which is you can optionally specify what the visibility should have been if not for testing, and this allows tools to catch unintended access from within production code. Perfect! This is exactly what we want to do when we make something testable, is make our production code bug-ridden. And so it's easy to pick on this particular example, but there are a lot of meatier ones that are actually far more important. The visibility of any one function probably is not going to bring down your service. But in the post where he coined this terms, actually he cited an entire architectural pattern that was created with the intention of making it testable. And in some ways, this is OK, because testable code often aligns with maintainable code. But that is not a fully overlapping Venn diagram. It is not always the case. And so there are times when you can make code architecturally testable, and that can reduce its clarity and meaning to the people who are actually shipping the source code to users. Now, there are a couple other classes of test failures or test difficulties, which are that we sometimes test the wrong things. Now, this might sound like sacrilege because we should be testing everything, right? That's usually how people feel. And if you're supposed to be testing everything, then it's impossible to test the wrong thing because, well, everything. But I want to take a step back and evaluate this because, of course, the people who usually write unit tests are the same as the ones who usually write the product code. This usually goes hand in hand, that if you write product code, you need to write the unit tests and then you commit them together. Now, as such, this means that our tests are usually cementing instead of exploratory. If the person who is writing the code understood how it would fail, then they would probably not write it in that direct way. And so instead, when they write tests on the code that they also write the product source code for, they are cementing their ideology. They know that it works for certain cases. They have planned for certain failure cases, and so they are writing the tests accordingly. Now, this can lead us to problems. So if you operate in a business org similar to mine, you might have organizational structures like this, where you have a product org, and then you have an infra org. Now, the product org might be doing things like testing UIs, while the infra org might be doing things like maintaining frameworks that those product engineers use and consume. Both of these orgs can experience catastrophic failure. None of them are immune to this. But if you take the median failure for each org, it probably looks pretty different. In that, when I spent time on a product team, most of the bugs filed against me were things like the text view is not wrapping correctly, or it's not concatenating, or it's placed in the wrong area. Now, when I was on a platform team, I still am to this day actually, the bugs filed against me gave me a lot more gray hairs, like there's a race condition in your networking layer and this really crucial code is not being completed. And so these bugs have different magnitudes of impact on the user and different costs. And in my org, product engineers tend to run a lot of experiments. We are an experiment-driven organization. And so when their cost for a bug is at this level, and they are running a lot of experiments, then cementing an API can feel like a Sisyphean task, like they are constantly pushing a boulder up the hill. Because it is very common for product engineers in my org to ship a variant with 5 different experiments, learn from it for a week, ship another variant with 3 different experiences, learn from it for a week, ship 2, and then finally narrow in on 1. And so by design, their API is in flux. And if I am asking them to cement it into place at the same time that they are trying to mutate it, this clashes and it doesn't feel very good. And then lastly, well, actually not lastly, there are considerations, and you can weigh these off, but there are other ways that these might be dealt with. For instance, you can have things like experiment gates. And so the fact that we require product engineers to have the same testing criteria as infrastructure engineers can be an interesting choice. And I'm not saying that we shouldn't do this or that we should. I'm just saying that it's something that is worth thinking about. So this brings me to my last of the testing difficulties, which is that in any medium to large size app, the number of possible states that that app can take on in correct or incorrect ways is quasi-infinite. It's a Cambrian explosion that is constantly shifting in subtle and nuanced ways. And as such, many orgs have issues with flaky tests. And the problem, of course, with flaky tests is that they erode your confidence in your testing ability. Because if a test fails and it is not a real failure, then when you go and you hear a failure the next time, you are less likely to react to it. And so this, of course, slows down your response time and makes that test failure even worse than it otherwise would have been. Now, this leads us to a place where a lot of people have very complicated feelings about testing. Very few people would claim that it is their favorite part of the job, except for, of course, that one person who's a TDD advocate sitting in the back corner who would claim not only that it's the best part of their job, but that it will save mankind. I appreciate your opinions. And so this is actually the meat of what I'm talking about today. And I went ahead and constructed this pyramid of correctness. This is a pretty common construct in testing, where people will create testing pyramids. And I like to call this a correctness pyramid because it's not limited to testing. You'll see that it actually starts with defined specs. Those are not a testing format. The way this pyramid is laid out is based on ascending cost. And I measure, in my opinion, cost to be the time to figure out that a bug has taken place, and also the cost of fixing it to your brand or your developers, et cetera, et cetera. And so we can look through some of the examples, like for instance, if you're working in an IDE and you have type inference, the cost of discovering that you have the wrong type is very low, because as soon as you finish typing, well, you now have a squiggly line that tells you that it's wrong. You can usually alt-right-click and it'll fix it for you. Then we can move to something like manual QA, where you are employing a real living, breathing human and paying their salary and their benefit and their vacation days and their childcare, if you're in Europe. And it gets a lot more expensive, and also they only work 8 hours a day, and so this time to finding the bug is longer. And of course, the most costly here is production, because most people are not shipping their app very often, and so by the time you find out this bug has been introduced, it's weeks down the road, and you may have brand impact from shipping a bug to your users. Now, if we go back to the examples that I used earlier, which were unit and integration tests, we'll find that they live somewhere in the middle of the pyramid. And this kind of starts to make sense of all of those difficult areas that I was outlining earlier, where they are not the lowest cost option that we have for correctness. And so that means that there are going to be some costs associated with it. And it makes sense that people are reacting to the costliness of these techniques. Now, if you consider yourself a savvy business person, I like to consider myself a savvy business person. I've never run a business, but it's like a really nice delusion to have. So if you share that delusion, then you are going to look at something like this, and you're going to say, I see a lot of opportunity. And of course, the opportunity that I'm talking about is what would happen if we moved lower down this pyramid to something that cost us less. Well, it's funny because the things at the bottom of this pyramid all seem to be language and compiler related. And it would be so convenient if I was at a conference that was language and compiler related, wouldn't it? Yeah, so of course, this is exactly what I'm going to talk about today. And this idea is not new or novel. There are so many languages that lean very hard into the fact that languages can be used as correctness tools, and that they can aid us in our testing journey. So for instance, I have a quote behind me of ReasonML, and Facebook claimed that when they adopt ReasonML, their bugs dropped from almost daily to once a month. We also have languages like Idris, where the entire language is a proof. And so that's what I want to focus on today, and specifically what I want to talk about is nothing new. I'm not going to introduce like, oh, this is the one trick that you need to use with JUnit so that it works every time. Instead, what I want to talk to you about is how you're writing code already, what you're using in the Kotlin language, and how those constructs and those features of the language can affect your testing story downstream. So, if you know anything about me, or you stalk my Twitter, which I welcome, it will come as no surprise that I'm going to start with the type system and a rave. I mean, and if you subscribe to Jared Forsyth, he's a React developer, he has this very pithy definition of types, which is that types are things that can be used together. And as such, if you have type errors, what it means is just that you are trying to use something in the wrong place. Now, if that is not testing, I don't know what is. It sounds a lot like testing to me. And so, it gives us like these common things that we talk about all the time, which is that if you unwrap something in the wrong way, you get a warning. But what I want to zoom into is actually something far more basic than that. I feel like I have support here. Like, someone's like playing the soundtrack of my life. It's not the song I would have picked. I think I would have gone with like AC/DC something, but I'll take it. Beggars can't be choosers. But I want to look at something far more simple, which is this method declaration. Like, just we are defining, a simple method and another rave. And and what's really interesting about this method declaration is that there's a lot going on because we're working in a statically typed language. So just on this one line, the type system's doing a lot of heavy lifting. For instance, it is guaranteeing that you are passing the right number of arguments. And this sounds so basic because most of us work in statically typed languages, but a lot of people cannot take for granted that if they ask for 3 arguments, they're going to get 3 arguments. And further, when we get those 3 arguments, there's this other layer where it's checking that all of the nullabilities and the types of those match up to what we would expect. And so in that case, if we wanted to use pseudocode to represent what was going on here, it would look something like this, which is this series of, am I getting the right information asked repeatedly and asserted against? And of course, we can't actually make this run if any of these tests fail, but you can see that this really is a testing framework. We take it for granted most days, but under the hood, there's so much going on. And indeed, I would posit that if you squint in exactly the right way, you would be able to see that type systems, and strong type systems in particular, are actually the ideal form of TDD. Now, in normal TDD, you're expected to write the test before you write the functionality, so we don't quite achieve that. But the next best thing to that is that as soon as you finish typing something, the test is in place, and that's what we get with type systems. Now, also, these tests are always up to date, even when you refactor. And in addition, if you're using a good IDE, like the ones from IntelliJ, then you get this feedback immediately and continuously. This is a pretty ideal testing system. Now, even better than all of this is that when you use types as tests, you can't remove them. And I really, really love this quote. It's actually from someone who's an OCaml advocate and works at Jane Street. But it says, in an untyped language, you can do whatever you want, which includes the right thing. But in a typed language, you are forced to do the right thing. And that removes your memory as a dependency. So I think that's really, really powerful. And in addition, there's more. A couple months ago, I gave, actually it was only 1 month ago in London, I gave a keynote about the psychology of programming. And in that keynote, I cited a very famous study that many psychologists run on people. And it's called Dunker's candle problem. And what they do is they invite someone into their lab and they present them with this. And they say, hey, I have a problem with candles dripping on my table. Can you please affix this candle in a way that it will not drip on the table? And many people look at this and they have trouble solving it. They might think, oh, let me try to melt the wax and then I'll stick it to the wall. But then that doesn't stop it from dripping on the table. Now, if they tweak this in one very, very simple way, almost everybody can solve this problem. And what they've done here is they've moved those tacks out of the box. And the solution that they're looking for here is this. And so it makes sense that if you were overlooking the tacks in the box, you were overlooking the box as a solution, you would not be able to get to this destination. And so this really proves kind of the power of perception, where the way things are presented to you will strongly affect your output. Now, I would argue that the type system is doing exactly this. We always talk about Kotlin's story with nullability, but it hasn't done anything revolutionary here. When we were working in other languages, for instance, Java, we had the same tools at our disposal to correctly work with nullability, to unwrap things in the right way, and to make sure that we were acting safely. The thing that we didn't have when this was not in the type system was something to direct our attention and our perception of what we should be focusing on. And I don't know if you are like me, but I feel like now that my attention has been directed towards this problem, I think about nullability at a much higher level than I ever did when working in languages where it was not encoded in the type system. I think about what it means at its essence and what I want from it and when it should and should not be used in a way that I was not doing before. Now, this brings us to typeful design, which is actually what I talked about last year. I didn't call it this, but typeful design is the idea that given a strong type system, you can push many invariants into it, and then you can offload your memory as a dependency by having the type system itself do a lot of the checks that you would otherwise need to do. So if you're interested in this, I would encourage you to watch that talk from last year. I'm not going to go too far into it because I did spend an hour on it already. But what's really interesting about typeful design is that it's so dependent on the language that you use. Now, if you don't believe this, I'll give you an analogy with English, which is my first language, my native language, and which causes me to be unable to express some really key things in my life that other people don't have a problem doing. So, for instance, there is a German word that encapsulates the feeling when you think of a really clever reply, but it's too late because you already walked off. Now, there's also a Japanese word for that moment when you go into a bookstore and you see a book that you're so excited about, and you buy it, and you run home, and you're going to read it, and then you put it on a pile with all the other books that you haven't read because you don't have time. And then, of course, there's this word that I tease Chet about, which is what happens when you hesitate when you're introducing someone because you've totally forgotten their name. Yeah, this happens to me a lot. And the interesting thing about all of these is that I used a full sentence to describe them to you. And if anybody in this room is a native German, Scottish, or Japanese speaker, I guarantee that they would say that I didn't correctly capture them, that there is some nuance that was just a little bit off. And that's because I'm using a less expressive language in this regard to try to capture this idea. And so I'm getting close, but I'm not quite there. And so if you are coming from, say, a language like Java, and you are converting code into a language like Kotlin, I would make the bold argument that I will only make in this room because we are all among friends, that Kotlin is a more expressive language than Java. Don't tell them I said that. And if you subscribe to this, then it puts a new perspective on the term Java-y Kotlin. I have nothing against that. If you want to Control-Alt-K, convert your file, that's fine. But what I would argue is that if you are going from a less expressive language to a more expressive language, and the only thing you're doing during that conversion process is getting rid of compilation errors or removing double bang or doing other minor cleanup, you're leaving a lot on the table in terms of this language was written in a way that it couldn't express some ideas, and so maybe they had to be encoded as unit tests. And if you are not taking the opportunity while you're rewriting that file to make use of the tools at your disposal, you're leaving cost on the table. You're making testing more difficult than it would need to be. And this is particularly important because of something that's captured really well by this other quote from Yaron Minsky, which is this. Type systems have a sort of snap-into-place feature, where if you've architected the types well and the program compiles, then running one or two examples will usually flush out most of the edge cases or errors. As such, they can amplify other forms of testing. Now, related to this is a language feature that probably most of us use when we're writing our daily Kotlin, which is algebraic data types. This is a fancy way of saying a type that is made up of other types. And specifically, something as simple as enums are actually a case of a sum type, which is a kind of ADT. And Kotlin, of course, has enums, but it also has enums++, which are like sealed classes. And if you're not quite sure what a sum type is, it's pretty simple. Mathematically, it's just a disjoint union. And again, fancy words, but what that means is that these colorful shapes are actually a sum type for this gray square in the middle. And that's because they cover the entirety of the square and they do not overlap. So they cover all of the possible sphere, but they don't overlap. They're a disjoint union. And like I said, enums fall into this case because you can only take on one instance of an enum at a time. You can't be two versions of the enum at one instance in time. And they're basically a sum type backed by an int, whereas sealed classes have the same properties, but they're backed by arbitrary data. The reason arbitrary data is really important is it makes this concept really flexible enough to scale up to a larger system. And so, what does this have to do with testing? Well, if we revisit that quote about snapping into place, there's something that I left out, which is that the reason things can snap into place is because they limit possibilities. So if you're working in a dynamically typed language, you might have a field like this. And this field could take on any possible point on this continuum. There is no information that we have just yet. If you go into a statically typed language, you can assign it some type, and that spectrum gets a little bit smaller. Now, there are discrete values it can take on. They're still quasi-infinite in the case of string, but they're there. Now, if you get into something like a sum type, say an enum with only 3 cases, this gets a lot more limited. Here it is very clear how that snapping into place effect is taking place. We only have 3 things. It could be one of those 3. Our options are severely limited. Why is this important? Well, if we're making use of enums and sealed classes in the code that we're writing every day for source, then if we have some item under test, then as long as we test the individual components of it, which are all smaller and simpler than the whole, presumably, then we can say concretely that we have thoroughly tested this item itself. And you may say, well, I get that in normal testing, even if I don't make use of enums and sealed classes in my Kotlin code. I can test these things on their own and still get this. And it is true. You could, if you wanted to, test the entire test domain using traditional methods. But it's more likely that you won't. And even if you did, you wouldn't have the same guarantee at a type level that you had done this correctly and in the most efficient way possible, with no overlap. And of course, this probably seems, you can understand why this seems like a good thing. But there's something else about the traditional testing method where you don't have these type guarantees that's costly as well. And it goes back to that English language equivalent that I gave you, which is that when you cannot express these guarantees, you reach for something else that's an approximation. In most of our industry, that's something like this. We have requirements that 80% or something similar of the lines of code must have been traversed in testing. Now, this is patently ridiculous in my mind because I don't care that a test traversed a line of code. That says nothing about its correctness. But the reason that we do things like this is because we can't express ourselves in a better way, in the way that something like a sum type would let us express a contract that everything had been tested in a disjoint union. And again, there are real costs to this. Things don't come for free. We can sometimes cause harm if we try to point people against a goal, like lines of code tested, and our real goal was something else. Then when they're pursuing this, they might be causing harm when we didn't intend for that to happen. That brings me to the case of immutable state. Now, I air quote and physical quote around this because, of course, the immutable story in Kotlin is pretty complex. We really have read-only more than we have immutable. And we don't have quite the same guarantees that other languages give about, say, structs in Swift. But if we pretend that we have immutability, if we treat something as immutable, then it opens this entire line of reasoning. And first, I want to just call back to where I started, which is that unit tests tend to test a single isolated object, whereas integration tests usually test a boundary. And the reason that this is important and that I want to hark back to it is that if you have mutable state, it is a form of communication. Now, hopefully this makes sense, but if not, we can run through the traditional counterexample, where if you have some global state and someone increments it, and then someone else comes along and they read from that, then they now have this updated state. And of course, it doesn't look like they're in communication with each other, but where did this one come from? Well, certainly it came from this other object. So whether we want to see it this way or not, these two things are communicating together. And because they're communicating together, then to test them separately would be something of a farce. Sure, we can do it, but we don't have the guarantee that we're going to want. And we certainly don't have as strong of a guarantee as if we could pretend that these things were completely separate and reason about them in silos. And so what this means for us is that we take this simpler form of testing, and usually faster form of testing, where we're testing isolated data, and we elevate it to this level where we have to test across boundaries, and we have to start coordinating things to get the same correctness paradigm. And this is, as you can imagine, more costly. Now, how does this play out in how we write code every day? Well, Kotlin as a language supports two feature sets, or two types of programming. It supports OOP and it supports functional programming. OOP is traditionally, it emphasizes encapsulated state, and normally that encapsulated state will be mutable. Of course, functional programming usually does the opposite. It usually stresses things that are pure, and by the definition of being pure, you cannot be reaching out to global state. So what does that mean for us? Well, if we write something that is pure, for instance, here's like an example property test of a pure function, then we can make really strong guarantees around it. For instance, this one, that for any given seed, if I run these two functions, they will cancel each other out. If we instead decide to use mutable state, some mutable global state, we really undermine the assertions that we can make about correctness of our code. Here, if we want to make that same assertion, we need to add an if and only if statement, in that this is true if and only if nobody else has modified this in the meantime. Now, this is particularly pernicious for three key reasons, which is that, one, this if and only if statement is necessary to correctness. If you forget this, you are going to be wrong. Two, it's usually hidden by testing, because unit tests will usually run these sequentially, and nothing else will have mutated it, even though it's possible for something to do that in your production app. And three, it's not generally a contract that you can actually enforce. You might leave a comment saying that this is your intended functionality, but you don't have a tool to enforce this among your peers. And so you can understand how this would get us into trouble. Now, the other thing that's detrimental when we choose to write non-pure functions in a testing sense. Obviously, there are very good cases to write non-pure functions. But the reason it can be detrimental from a testing impact is that when we have a pure function and we go to test it, then we can easily conclude that if the error, or if the output of this is wrong, the error lives somewhere in the test that we are running, the test function. And so what happens here is that we set out with an intent to determine something about this particular function. And in the end, we receive information about that particular function, either that it's correct or it's incorrect. And so this is good because we have intent and it matches what we are actually receiving. Now, if you live in a world where you are reaching out to other states, you can see how this would break down. Now, if I get an incorrect output, it could be because the thing I was testing was wrong, but it could also be something unrelated. So I have the intent to test A, and I am now receiving information about A union B. And this is not what I set out to do. Maybe that information is still useful. It probably is, but it's not what I wanted. It's not what I asked for. So this can make our testing story more difficult. As such, I would like to amend the earlier quote, which said type systems amplify testing, with my own addition, which says pure functions amplify testing. And again, there are so many good use cases for side effects. I'm not saying that we should all sit here and never write a side effectful function. But what I am saying is that there is a really, really great testing story for pure functions that is not there for their corollary. And as such, if we have the choice to use both, and it doesn't cost us very much one way or the other when we're writing our source code to make this decision, it could be beneficial to err in this direction. Now, that brings me to interfaces. You knew I had to go here because, of course, we use them in our code all of the time, and also they're a very hot topic for testing. A lot of times when people have trouble testing their code, it's because they haven't abstracted something into an interface. Now, interfaces are useful for several key reasons. One is that they contain a definition for some functionality in one place, and that's really, really useful. Two, they often separate that definition from the implementation of it. Now, this gets a little bit murky when you have default functions, where you could mix this into the same file, but generally speaking, we get some nice separating effects. And what this allows us to do, specifically in testing cases, is something like this, where you can create something for your production app, and you can create something for a test environment, and you don't really need to change the call site. Now, this is not the only reason that they're helpful. There are plenty of really good production quality reasons to use interfaces outside of that. But given that this is a test on talking, this is what I want to focus on. And so there's a quote that I really, really love. And I've already talked about people who work in JavaScript and from OCaml. And now I'm going to actually quote the person who maintains Swift's standard library, because he gave a quote about protocols and how they relate to testing. And protocols are just a beefed up version of interfaces. And what he said was this: "This kind of testing is really similar to what you get with mocks, but it's so much better. See, mocks are inherently fragile, right? You have to couple your testing code to the implementation details of the code under test. And because of that fragility, they don't play well with Swift's strong static type system." I may remind you, Kotlin has the same type system, same strong static type system. And the conclusion there is that protocols give us a principled interface that we can use that's enforced by the language, but still gives us the hooks to plug in all of the instrumentation that we need. So again, this is an example from Swift, but it perfectly applies to our day-to-day work in Kotlin as well. And really, the heart of this matter is that if we are accurately using interfaces in our source code as we're building out examples in a day-to-day repository, then what we get to do is we get to move from testing and implementation to testing output. Now, I've represented testing output as a black box. And I was a little bit nervous about that because people have really bad connotations with black boxes. And that's usually because the people in this room are trying to debug them. And it turns out when you're trying to debug a black box, it's really difficult. But I think that this is unfair because black boxes are actually really, really great in almost every other regard from debugging. For instance, The best possible case of black box magic is a genie. What you do is you pick up a lamp and you rub it, and the genie comes out and they say, "What do you want?" And you tell them, and they make it come true. You have absolutely no idea how they made that elephant appear in your bedroom, but they did it, and you are delighted. And that is a form of black box. You don't know how that machination worked. And of course, most of the world runs on this. For instance, if you go to an Apple store or a fine dining experience, they are striving with every ounce of effort to make sure that you do not notice any of the hard work they put into making your experience as good as it is. They are deliberately trying to hide all of this effort. Because when you're at Noma eating something tasty, you don't want to be thinking about the people cleaning the pots and pans in the back. That takes away from your experience. And moreover, you really don't care if Susan or Sally chopped your vegetables, as long as your vegetables are really tasty when they come out on the plate. And so I would argue that this is very much true for people who are consuming your code as well. If you define correctness, and it is key to define correctness in a comprehensive way, so that includes performance, that includes regression tests, that includes the fact that the unit itself is working. If you have a comprehensive definition of correctness, and you have an item that meets that comprehensive definition of correctness, then does it really matter to you how it did that? I would argue that in the vast majority of cases, the answer is no. And if we ignore this, we pay some costs for it. Specifically, if we decide that we want to code against an implementation instead of an interface, then when it comes time to make change, that change is harder and it is more dangerous. Specifically, it is harder because when you change the implementation, you now also need to change the tests. And additionally, when you change the tests at the same time that you're changing the implementation, it means that you're giving up safety. The idea of tests was to kind of solidify this API so that things could move out from under it, and you would still have this contract that you knew you were supposed to meet. And if you're changing that, well, you lose that level of safety. So, all in all, I haven't covered anything revolutionary here. I've talked about thinking of ways that we can push invariance into the type system, thinking of ways that we can make use of sealed classes and some types to limit test domains, keeping an eye on pure functions and immutable states, and using interfaces effectively. And these are all things that should be familiar to you. Nothing here is probably something that people in this room have not already used in their code. And what I'm lobbying for is that when we use them mindfully in order to tie into our testing story. Because, of course, they have all of these other purposes, but they can also make testing so much easier and maybe alleviate some of the problems and some of the difficult feelings we have with testing. But, of course, every testing system, protocol, etc. that you rely on with anything useful, like, I don't know, your life, has redundancy built in. This is how testing works in the real world. And it's because this is how math works in the real world. We'll never make something completely fail-proof. And as such, the best we can do is we can create redundant systems so that probabilistically we can drive the likelihood of failure down to 0. With that in mind, by giving this talk, I don't want anyone to think that what I'm meaning to do is chop off the top of this pyramid. I have no intent to say we can do everything we need to do on a correctness paradigm at this level. Instead, what I hope you took from this talk was the fact that we have many tools available to us for correctness pursuits, and that they all have costs. And if we are already writing code and we are already using a language that can help us in these pursuits, we should leverage it. I think this is all summed up best by this tweet from Matt, which basically says, every time we encounter an error, let's look at how we can move it one level down the cost hierarchy. I hope today that by attending this talk, you have some ideas for how you can use Kotlin to do that. That's all I have for you today. Thank you.